maintaining equilibrium established in a 2-liter flask at 30 degrees Celsius. And I've got my reaction right here. And I could not get delta to show up, so I just wrote it out here. Delta H reaction equals minus 41.2 kilojoules. And let me zoom in here. There we go. My first question for you is this reaction endothermic or exothermic?
Exothermic.
Thank you, Daryl. It is exothermic. Heat is given off by this reaction, and we can think of heat as a heat or energy as a product. Let me write out my reaction with that taken into account. Which we've done before. So we have, so this is plus 41.2 kilojoules given off by the reaction. It says, what will happen to the concentration of CO2, which is right here, if the temperature is decreased? Now, this question and the fact that it says decrease, increase, or not change tells us that we're dealing with something called Le Chatelier's Principle. And you do not have to know the name, but I do refer to it as Le Chatelier, even though it's pronounced Le Chatelier, or spelled Le Chatelier, typically pronounced Le Chatelier, since it's French. And what Le Chatelier's principle says overall is that when a stress is applied to a reaction, the reaction counteracts that stress. When a stress is applied to a reaction, and I forgot a part here, I'm going to add it back in, at equilibrium, the reaction counteracts the stress to establish a new equilibrium. To establish a new equilibrium. Now, the way this works is there's going to be 3 different things that you can do. You can change the temperature, you can change the concentration, and you can change the pressure. Now, this one happens to be the temperature one, and the way the temperature works is that if the temperature is decreased, that is equivalent to saying that heat is removed. Because, and we'll talk through this, but Le Chatelier's principle uses typically it needs no numbers. It's all about the trend. So, if temperature is decreased, that's equivalent to saying heat is removed, because that's how you lower the temperature. You remove heat. That's something that is not necessarily a connection we've made in this class, but hopefully you're okay with that. And if not, jump in and we can talk more. Temperature is decreased is equivalent to saying heat is removed. Heat is a product of the reaction. So we are removing a product of the reaction. All right. Any questions about that? Because the next part is the Chateliers Principle part, and this is all just understanding the stress. Like, we change something about a reaction, and the question is, how does the reaction respond? So we removed a product. When you remove something, the reaction makes more of it. So we removed a product. So the reaction makes more of the products. Meaning that it will then make more of all of these products. It will make more carbon dioxide. It will make more hydrogen. It will make more heat energy. Now we can answer our question. The question says, what happens to the concentration of CO2? It will increase. So here, CO2 concentration increases. And that's going to be pretty much the logic stream for all of Chateliers Principle problems. Take the reaction. If it needs be, put heat into it as either a product or a reactant. And then think about whether the heat was added or removed. And then see the effect on the reaction. Any questions about that?
Professor?
Yeah, Daryl.
What if it was an endothermic reaction? What happens to the products then?
Great question. So let me do a counter example that I think illustrates that. And it'll just be a generic one. It says A goes to B, or here. A goes to B, and this time it's endothermic, okay? That means that we can write the reaction with energy as a reactant. And let's suppose, just like above, the question is, what will happen to concentration of our product if T is decreased? Now, so our logic stream still goes, T is decreased, equivalent to saying heat is removed. Heat is a reactant, so T decreased. Heat is removed. Heat is a reactant. So the reaction makes more of whatever was taken away. That's what I mean by counteracts. So reaction makes more of whatever was taken away, so it makes more reactants this time. Now, when it makes more of the reactants, what happens to B?
I wouldn't say the concentration decreases.
Thank you, Daryl. Very good. Concentration of B decreases. Because that's one of the secrets of this is, so the reaction is responding. The reaction can go in the forward direction, like the example up here, or the reaction can go in the reverse direction, which would decrease the concentration of B right on. Does that answer your question, Daryl?
Yes, Professor. Although I'm thinking,
Yeah.
what if heat was removed, and what happens to Kc?
Oh, great question.
Does that affect the rate of the react? Well,
Yes. Okay. So you mentioned rate, and we know from last lecture outline, that rate of reaction definitely depends on temperature. And as temperature goes down, rate of reaction goes down, always, right?
true.
Now here, we're not talking about rates of reaction, we're talking about the equilibrium constant, big K. And for big K is a function of temperature. We've said that, I've said that in the videos, and now I'm saying it in the homework videos as well. But big K as a function of temperature is a little harder to get our heads around, but we can think of it in terms of Le Chatelier's principle like this. So let's do this example that we just talked about now. If T is decreased, so and let me do a third, so T is decreased. So now we know what's happening to temperature. We said heat is removed, so the reaction makes more of the reactants. If at the new equilibrium there are more reactants, what can we say about the new K value? If there are more reactants. And we know, and I know this is all very new, and I'm happy to take you through.
It will be less than
yes.
0.0.
Sorry, I just totally did that backwards because I was thinking about something else. There we go. So if T is decreased and heat is removed and the reaction decreases the numerator of this and increases the denominator, the new K value will be smaller. Right on. And we don't know how small, right? This is a qualitative, meaning no numbers approach. That's how Le Chatelier's principle works. But yeah, I mean, I think it's really interesting actually, because now we can talk about not only how fast the reaction goes, but where is the position of equilibrium, and we can control it if we change the temperature. Sorry, Daryl, I jumped in there. Go ahead if you have a question.
No, I get it now. I understand what you're saying.
Yeah. I mean, this, and so my background's in chemical engineering, and this is where my ears really perked up. It's like, all right, some reactions, and specifically exothermic reactions, if you, let's say this, if you increase the temperature of an exothermic reaction, it's going to, so you're going to add heat. The position of equilibrium actually makes less products. So for exothermic reactions, if you increase temperature to get a faster reaction rate, to get the reaction over with sooner, you're actually hurting yourself by taking away some of your products. And so there's an interplay here between what the position of equilibrium is and how fast you get there, and you've got to consider both. Anyway, but that's for chemical engineers who are, but in the end, you can think about this in terms of lots of ways, like even concrete's forming time as a function of temperature. So anyway, any other questions about this? Let me see. So So there's another one. Yeah. Um, anyway, we haven't talked about concentrations. So for concentrations, if you increase the concentration of CO2, the reaction shifts away from it. If you increase the concentration of CO, the reaction shifts away from it. So concentrations are relatively easy, I think, in terms of Le Chatelier's principle. Heat is a little more complicated, and pressure is a little more complicated.